Hey guys, this is Thomas Cocker with the BCA, and I'm here with my ecstatic coworker, Chris Pilot. Say hi, Chris.
Hello.
All right, so today we're going to be talking about mixed air temperatures, how you calculate them, and specifically through a series fan-powered terminal unit. And as you can see here, we've got a blue arrow, a red arrow, and an orange arrow. What do they mean? So the blue represents the supply air being delivered by the air handling unit, and the red arrow represents the return air that's coming from above ceiling, and the orange arrow is the mixed air temperature between the two. Then let's put some numbers to it. Typically, supply air is being delivered at 55 degrees. Obviously, if it's being delivered colder or warmer, you would just put that number in there. And then I just put in some rough CFM values just to make this calculation a little easy. Then the return air, that could be anywhere from 68 to 75, 77 degrees. I just kind of picked one in the middle, 72. And then that 700 CFM is going to be pulled in through the return. And then the mixed air is what we're going to be calculating. And so obviously, if you have 300 CFM coming through your primary, 700 CFM coming through your return, then the result mixed air will be 1,000 CFM. And so,
1,000.
How did I get 1,000?
It's a joke. Please move on.
It's a terrible joke. So before you do your calculation, it would be ideal to kind of have a rough estimate for where your calculation will land. Obviously the air is not going to be colder than 55 if you're mixing it with, warmer air. And then obviously it's not going to get hotter than 72 if you're mixing it with colder air. So if your middle point is 63.5, so if you had an equal amount of 55-degree air and an equal amount of 72-degree air, then you'd be at that 63.5. But in this case, you have more warm air than you do cold air. So you're going to be over to the right of that 63.5-degree line. So you're going to be roughly, 67, 68 degrees. So with that in mind, you can do the calculation and know that if you inputted something wrong, you're going to be really far away from that, then you inputted something wrong and you can redo it. So the equation that we're going to be using is the mixed air temperature is equal to temp 1 times its CFM ratio plus temp 2 times its CFM ratio. And putting numbers into that is that 55 degrees times 300 over 1,000 plus 72 degrees times 700 over 1,000. And then you could also do the calculation. If you don't have that 700, you could easily just do 1 minus 300 over 1,000 and it'll give you the same result. So putting that in or calculating out the ratios, it's going to be 30% of the 55 and 70% of the 72 is going to equal 66.9 degrees. And so, yeah, I mean, basically what we estimated, I think I said 67, 68, we got 66.9. So pretty darn close. You can almost do this stuff in your head.
Almost like you made that and knew what the answer would be.
Almost like it.
Almost.
So now that we have our mixed air temperature and we're going to be able to calculate the rise across a heating coil, we're going to use the same numbers. So then the red arrow represents the rise, and putting numbers to it, you're going to have that 66.9 degrees.
Now I'm just confused. I'm confused.
Yeah, well, that's not hard. So now you have 66.9 degrees entering with 1,000 CFM, and obviously the air entering is going to equal the air leaving. And then we have a 5.73 kW heater. Reason I did that is just to make the end number, kind of exact. So no one can hear you, Chris. If you look at a typical schedule, it's going to look like this. It's a series fan powered box. So it shows your primary air when the box is at neutral. The air coming in from the air handler is going to be the air exiting. You're going to have no return, and that's going to be 1,000 CFM. Then the minimum air is going to be 300. So that's when you're going to be introducing 700 of the return air to make up the full 1,000 to get discharged. like we showed in the previous slide. And then typically for a reheat coil data, they're going to give you the kW of the heater, typically the entering air conditions, how much CFM is actually going to go across that coil. And then sometimes they'll give you the leaving air temperature. And if they don't, now you'll know how to calculate it. So you need to first convert your kW heater into BTUs, because typically the sensible heat equation.
Yeah, there's two other things you're not really mentioning. Like if you're commissioning a project with a lot of terminal units on it, like we all do, you can get a quick idea of the discharge air temperature sensors if they're functioning properly or even close, is in the ballpark. And the other thing is you can tell if balance was properly done, because if you're discharging, 55-degree air at the terminal unit discharge air, then and you're not in full cool, obviously there's some kind of problem. Or if you're in full cool and discharging 65-degree air, that's going to tell you there's some type of issue, possible balance.
Right. Exactly. There's a lot of reasons to do this mixed air temp calc and also do your calc across the heating coil. Like Chris mentioned, it's invaluable in the field, and then also prior in the design process, because it can help you find design issues, before you get out there, before boxes are ordered. So continuing on, once you get your BTUs, you can then use your sensible heat calculation, which the reason you're using sensible heat is because typically when you do a reheat coil, you're not going to have any latent gain, right? You're not dropping out moisture from the air. If anything, it could gain moisture. And in this case, we don't have a humidifier involved, so you're not going to be gaining any moisture. And then technically total at this point would equal your sensible. So you could use that one as well. But obviously the sensible heat is a lot faster. So you have your temperatures, you have your BTU, you have your CFM, so you can calculate this one for the second temperature. So the equation is the BTUs, which is converted from the kW, divided by 1.08 times the CFM plus temp 1, which would be that 66.9 degrees. So if you plug those numbers in and solve, then you'll get 85 degrees Fahrenheit. So 85 sounds low, but actually that's a pretty good temperature. It helps get a good amount of throw off your diffusers. You can go up to 90 degrees, but when you start to get above that, your throw actually is impacted. So I wouldn't go much higher. So if your box is discharging 110, 120, you're getting really hot, and you need to find a way to reduce that temperature, either by potentially increasing the airflow or not allowing so many stages to come on, or if it's an SCR, just max out the percentage that it's able to command that coil to. A lot of ways to get that temperature back down. All right, well, thanks for watching. If you like that video, please hit the like button. And if you want to see more, please subscribe. And remember, when it comes to mixed air temperature calculations, never, under any circumstances.
You need outtakes at the end of the video.
Hey guys, this is Thomas Cocker with the BCA, and I'm here with my enthusiastic coworker, Chris Pilot. Say hi, Chris.
Hello, Chris.
I don't know what else to add.
I don't know. Probably should add more. At least 12 people will hear this.
You're probably right.